Hello physics students, in this video I want to walk you through how to solve for a quest problem. Number 15 is the example I'm going to walk through in this video. The numbers will be different for your quest, but you can use these same techniques as you're walking through and checking your answers and also solving out the problem for the quest. The big idea in this problem is to find some key energy relationships, and so I'm going to walk you through what those look like using this example. We have a person on a swing, and they're giving us some information about the swing. We know the height off the ground at the highest part of the swing, and we know the height off the ground at the lowest part of the swing. And then we want to figure out what is her maximum speed. Okay, so where is she going to be going the fastest? All right, so that's what we're going to be calculating. Max speed. All right, so let's just think about that question for a second. Before you even start with any numbers or start with any math, just think of somebody swinging back and forth. Where will they be going the fastest? Hopefully you're answering to yourself, they're going to be going the fastest at the bottom of their swing, the bottom of their arc, okay? Well, we know there's some energy relationships here that we need to be paying attention to help us figure out what that velocity would be at the bottom. And one of the things that's key is whatever energy we have, total energy at the top of their swing is equal, so the top of the swing would be right here, is equal to the total energy at the bottom of the swing right here. Okay, so we want to figure out and identify that energy relationship by identifying what kinds of energy are happening at those particular spots, and then work backwards to figure out the velocity. Now, I know just from experience that one of the energy that will help us discover velocity is kinetic energy, so we're going to come back to that as well. All right, so let's think about the energies that they would have at the top, all right? And I'm just going to write out the full energy equation, and we'll decide if it applies or not. For mechanical energy without friction, and that's a key thing in this problem, there is no friction. So when we take a look at the energy, we have kinetic energy. I'm going to put a T for the top, and that combines with any potential energy that would be at the top, and I'll put another T there, so potential energy. And then that is going to be equal to the energy at the bottom. All right, so let's use a slightly different color for that. Let's use orange. And again, at the bottom of the swing, there could be some kinetic energy. I'll put a B for bottom, and there could be some potential energy. And we'll do that at the bottom as well. So potential energy here. Okay, so we want to find out what those equations are for each potential and kinetic energy, and then see where that leads us in determining the speed at the bottom. All right, so let's think this through. In our energy relationships, we know right away from the beginning that the top of the arc, they're temporarily at rest, so the velocity would be 0 here. So therefore, there's no kinetic energy, so that term drops out, it goes to 0 at the very top. And at the bottom, if they swung all the way to the ground and were touching the ground that whole 2.8 meter distance, well, then we would have a potential energy of 0 at that part, but there isn't. There's a little bit of height there. So on this side, we need to keep both these terms. We know they're going to have some kinetic energy as they swing through the bottom. They're also going to have potential energy because there's still some height at the bottom of their arc. All right, so let's plug in what we know about this. Potential energy is going to be the mass times the acceleration of gravity times the height. And I'm going to put a T there because I know that's the height at the top of the situation. And then when we go here for kinetic energy, that's 1/2 mass times velocity squared plus the potential energy, m times g times height, and I'm going to put this height at the bottom, okay? Now that's information they've given us. We know the height at the top and we know the height at the bottom. Energy they haven't really given us is the girl's mass. Now what's interesting about that is this actually has mass on both sides of the equation. You can see it here, here, and here. And when the same variable shows up that way, we actually can cancel the mass out. So I'm going to rewrite this without mass because it really doesn't matter for our equation. So if we know the gravity and the height at the top, we know both those quantities, that's equal to the 1/2 times the velocity, and this is the velocity we're solving for, that's the velocity at the bottom, squared, plus g times h at the bottom. All right, so from here I can really kind of work through and solve these out even just a little bit more. So I'm going to rearrange this. So I now have my equation will look a little bit like this. So I could plug numbers in at this point, or I could just continue algebraically. I'm going to go algebraically a little bit farther here, and I'm going to move this over to the other side. So I have GHT minus GHB equaling 1/2 V squared. I can even simplify this a little bit, factoring out the G. I can have HT minus HB all equaling 1/2 V squared. This times 2 now, so 2G, the height at the top minus the height at the bottom, all equaling V squared. And then finally I can take the square root of both sides. So I get the square root of 2 times G times the height at the top minus the height at the bottom will equal my velocity that I'm looking for. All right, plugging in some numbers. Square root of 2 times 9.8. Now I know the height at the top was 2.8. So 2.8 minus 0.7, both in meters. And that's going to equal my velocity at the bottom. Okay, and running the calculations, I end up with about 6.4156 meters per second as my velocity. Now that comes back up to what we're solving for, the maximum speed at the very bottom of the arc. And I know it's going to have maximum speed at the bottom because that's where it would have the highest kinetic energy. All right, so those are some ways to solve these problems. The big thing to come back to is what is the energy relationship for that particular problem, and you're going to be developing them as you read through and understand how the problem works. So they might have different energy relationships depending on what's given. All right, thanks and have a great evening.